My name is Jose Ayala Romero. I'm a senior research scientist at NEC Laboratories Europe, and today I will present our paper published at IEEE Infocon 2026 with the title SPIFF, Selective Preservation of Image Fidelity for Bandwidth-Constrained Heterogeneous Networks. This work has been done in collaboration with Marco Balena and Carla Chiaserini from Politecnico de Torino and CNIT, and Andrés García Saavedra from NEC Laboratories Europe. This is the outline of the presentation. We will start with some background and motivation, then I will provide the summary of the contributions. After that, I will detail the proposed solutions. It has three parts: a SPIFF framework, bits problem, formulation, and learning-based decision engine. Then we will show some evaluation results, and finally we will end the presentation with the conclusion and future work. As a background, this is our reference scenario. The idea is that we will transmit images through a network, which is the following. On the left, we have the source of the information. We can have some IoT devices that send images to a gateway. Also, the source could be a satellite that directly take pictures from the space. And these images will be sent to the non-terrestrial network that could be one or several satellite nodes. After the non-terrestrial network, the image is forwarded to the distribution network. This distribution network will have some computing power that will be used for reconstructing images, as we will detail later. And then after the distribution network that could have wired and wireless links, this will be delivered, the image will be delivered to the end user. This architecture has many challenges. We have asymmetric computational capabilities. We don't have the same computing power at the transmitter compared to the receiver. The bandwidth is limited. This is related to the NTN. We might have strict delay requirements. This is related to the application in particular we consider. And of course, the network conditions vary over time. Indeed, in this context, semantic communication could be an interesting approach, because with semantic communication we can compress a lot the information we send. However, when we use this kind of compression, we might worsen the perceptual fidelity of the image. So we have this trade-off between perceptual fidelity and bandwidth saving, which is one of our motivations, as I will explain later. So the motivation of this work is that different regions of an image could have different perceptual relevance. Okay, so I will illustrate that with one example. So we see on the left what we call the source image. This is an example image. We see a train in a train station close to the woods. And for this example, we will assume that the important parts of this image are the train and the railways. This is illustrated in the second image called regions. We see in yellow the important, the high relevance regions of the image. Then let's assume that we use a traditional semantic communication method. This method consists of getting the caption of the image, sending the caption through the network, and then reconstruct the image from scratch at the receiver. And in this case, we will get something that we have in the middle image, the SEMCOM image. In this example, we save a lot of bandwidth because we only send the caption of the image. However, we fail at preserving the important parts of the image. As we said before, the important parts of the train. The train is completely different, and therefore we fail to satisfy this objective. So this is the main idea of our work. So we want to preserve the relevant parts of an image. And on the right, we have two examples of applying our solution. We see the two right images with the name SPIFF, which is the name of our pipeline. Basically, we see that the important parts of the image are successfully preserved, but the non-relevance part of the image are reconstructed with different levels of accuracy depending on the bandwidth we want to save. So if we save more bandwidth, we will reconstruct the non-relevant parts with lower perceptual fidelity and the other way around. So yeah, this is the main idea of this, the main motivation of this work. So we want to keep the high relevance regions of an image and transmit the rest of the image with a conditional perceptual fidelity depending on the application and on the constraint of the objective of this application. We wanted to further study this across different datasets. We consider the general purpose COCO datasets and also some task-specific datasets like related to satellites and UAVs. And we wanted to study the fraction of pixels with high relevance in these datasets. We observe the distribution on the figure, and we see that different datasets have different distribution, but also the fraction of high relevant pixels varies a lot across images. For example, we see in the COCO dataset that the distribution is very flat, meaning that we have important variations within the images of the dataset. This motivates dynamic optimization. So fixed configuration wouldn't be effective because, as we see, the difference of the high relevance pixels regions within the images varies a lot. This work has three main contributions. The SPIFF framework, which is a pipeline that processes the image. This pipeline needs to be configured, and that's why we formulated the bits problem. The bits problem formulates how the SPIFF framework should be configured over time. And finally, to solve the bits problem, which is very complex, we propose a methodology, a learning-based methodology to solve the bits problem and therefore to configure the SPIFF framework, which is this learning-based decision engine. We start with the SPIFF framework. We see here that it has two parts, the encoder and the decoder. We see many boxes inside, a lot of functionalities, but I will try to provide the rough high-level idea of this. So basically, in the decoder, we have the initial image, and then from this initial image, we see that in this example is a man in a park. We do the semantic segmentation. We extract the semantic segments of the image, and then from this segment, we select the high relevance segments. In this case, would be the man. And then once we have the high relevance segment and the mask of the segment, this part will be sent basically. And from the rest of the image, we select random patches, random parts of the low relevance part of the image, as we see here. And this is another part that will be sent. Optionally, we can compute the caption of the image, that this could be also sent, and we basically will have these parts to be sent. The high relevant part, the mask of this part, the patches of the low relevant part, and the caption. Based on this, at the receiver, you will partially recompose the image with the information you have so far, and then with a reconstruction model, you will finally reconstruct the image. You can inpaint the missing parts of the image, and you can also use the caption to fit the model. That could be a latent diffusion model, and then you can reconstruct finally the image. Later, we will provide more details about this pipeline. These are the parameters of the SPIFF framework. There are some parameters that need to be configured a priori and depends on the application, but I will focus on the ones that should be dynamically configured, that are the vector X. The vector X has two components, the parameter beta, which configures the bounding box. Once we select the high relevant segment, we need to set a bounding box around this segment, because we can only send, it's not efficient to send uh, shapes that are not a square, because we use JPEG and so on. So beta sets how big this bounding box will be. If beta is 0, the bounding box is perfectly fitting the high relevance segment. If beta is 1, we will send the full image, because we have expanded the bounding box to the full image. So this is a way to control how many pixels we send. And on the other hand, we have P, which is a vector setting the amount of patches we picked from the low relevance segments. And this is another way to configure the accuracy of the reconstruction of the receiver, right? So the higher the V, or the higher the values of the vector P, the more pixels we will send. We will increase the perceptual fidelity, but also we will increase the use of the bandwidth in the network. This is very important because we need to configure X for each image depending on the application and the goals and the constraints we have for this application. Now we provide more details about the pipeline. So this is the part at the transmitter. So we have the original image A, this man in the park. Then we do the semantic segmentation. We have the two segments, the person and the background. Then we identify the high relevance segment, which is the person and the mask of this segment. Then we do the patching. We select some random patches in the non-relevant part of the image according to the vector P. In this case, P has only one element because we have only one low relevance region. And finally, we put all the patches together in a patch grid, and this part will be sent to the receiver, with image C. At the receiver, we recompose the image with all the information we have. We have the high relevance segment, we have the patches, everything in the original position, and then we need to do the inpainting from this, and optionally the caption. We will use a latent diffusion model, and we will inpaint the missing parts, and we will reconstruct the image. So this is also a rough overview of our framework. And now we need to formulate the bits problem. Why? Because we need to know how to configure X. What will be the size of the bounding box of the image, and how many or how we select the patches of the image. So basically, we want to select X to solve this problem. This problem is solved per image. Basically, we want to minimize the number of bits we send, and we also have two terms. These two terms are related to the perceptual and semantic fidelity. This sum is across all the relevance rank, because we might have several. And then this term, this is related to the perceptual fidelity. We want the perceptual fidelity of image I for the given configuration to be higher than the perceptual fidelity minimum threshold, and this lambda is a penalty term. Similarly, we want the semantic fidelity of the image I for the given configuration X to be higher than the minimum semantic fidelity threshold, and this lambda is the penalty term. These two are soft constraints in terms of perceptual and semantic fidelity, and we also have a hard constraint in which we want the delay of image I for a given configuration to be smaller than the maximum delay that is set by the application. Solving this problem is very challenging because the fidelity measures are very random, are very noisy. Also, the end-to-end delay is stochastic because we cannot control the state of the network. the objective function is highly nonlinear, and also we might want to tune the lambda parameters depending on the application to weight differently the difference of constraints. So based on this, traditional approaches are not effective for this. What we do is we formulate this problem as a contextual bandit problem with instantaneous constraints, and we propose a learning-based solution that I will explain in the following slide. This is the architecture of the learning-based decision engine we propose. We have one actor and multiple critics. So the actor receives as an input the state of the state, which is related to the composition of the image, and the output is the vector xi, so the configuration for image I. To train this actor, we need a set of critics. So we have several critics because each critic will approximate different part of the objective function and the constraint. So for example, critic 0 will approximate the number of bits for every configuration, critic 1 will approximate the perceptual fidelity for one of the ranks, and so on. So once we approximate all the important parts of the bits problem, we aggregate all this information to get the cost function. This cost function will be differentiable, so we can backpropagate the gradients through all the frozen critics, and then we can train the actor. Some small details about this architecture is that the critics they don't approximate the mean values of the function, but they are distributional critics. We approximate the distribution of the function of each of the terms. Also, to train the actor, we use the deterministic policy gradient theorem to do the backpropagation. Now I will present some experimental results. Some details about the evaluation. We use the COCO dataset. We selected two semantic categories, person and other. And an important part is that for the satellite link, we follow the 3GPP guidelines to simulate the satellite link. As metrics, the perceptual fidelity is 1 minus the LPIPI's metric, and the semantic fidelity will be evaluated using the CLIP score. Both of them are well-known metrics in computer vision. Then, as benchmark, we will use traditional compression, JPEG, as a benchmark. Also, as a semantic communication benchmark, we will use the example I explained before. We will compute the caption of the image, we send it through the network, and we recompose the full image from scratch at the receiver. And lastly, as a benchmark for the machine learning part, we use the neural contextual bandit, which is a standard approach to solve this contextual bandit problem, and the objective is to evaluate how effective is our machine learning solution compared to a standard one. This first result is to evaluate the trade-off between the fidelity and bandwidth. So basically, we evaluate our solution against some benchmark, and our solution has some fixed configuration. We see in the figure, on the x-axis, we see the bandwidth savings, and on the y-axis, we see the perceptual fidelity score. We see that the semantic communication approach achieves the highest bandwidth savings, but the perceptual fidelity score is pretty low. We cannot reach close to 1 perceptual fidelity. On the other hand, we have JPEG that achieves the highest perceptual fidelity score, but the bandwidth savings are very limited. And we have in the middle our approach. We can, with different configuration of our approach, we can get very high perceptual fidelity values and also very high bandwidth savings. And the idea we want to show here is that our solution can flexibly navigate the trade-off between perceptual fidelity and bandwidth. We can adapt to different configurations depending on the requirements of the application. Now we particularize these results to different relevance ranks. We also show the trade-off between perceptual fidelity and bandwidth savings for low rank and high relevance rank. We observe that for the low rank, our solution with the different configurations obtains a slightly lower perceptual fidelity, but much more bandwidth savings. But in contrast, and very importantly, for the high rank, we obtain the same perceptual fidelity, also with some bandwidth savings. And this is very illustrative of what our proposal does. So SPIFF selectively degrades the quality of the low relevance regions, while we keep the perceptual fidelity of the high relevance regions. So in that way, we can maximize the bandwidth savings while satisfying the requirements of the application. Now we saw another evaluation result. For this evaluation, instead of fixing the configuration of SPIFF, we use the learning-based decision engine. Basically, we train this machine learning approach, and then after training, we evaluate this. And we evaluate this in 3 scenarios: strict, intermediate, and lenient. These 3 different scenarios set 3 different values, 3 different set of values for the constraints. So the strict scenario will have stricter constraints that are more difficult to satisfy. Basically, we compare all the benchmark. We can see, for example, that the semantic communication benchmark achieves the highest bandwidth savings, but the constraints are not satisfying most of the cases. In the case of the JPEG compression, the constraints are satisfied most of the cases, but the bandwidth savings are not the highest. In the case of the neural contextual bandit, NCB, in some cases it struggles to satisfy the constraint because of the limitation of this learning approach. And finally, we see the results of SPIFF, our proposal. We see that we get the highest bandwidth savings subject to the constraint as satisfied. So we can see that our solution can adapt the policy, the configuration of the system to guarantee the constraint satisfaction, while we also maximize the bandwidth savings. To finalize the presentation, we will discuss the conclusions and the future work. In this work, we propose SPIFF, which is a framework that overcomes the limitations of standard semantic communication approaches, and we introduce the concept of selective fidelity. We integrate the SPIFF framework with a learning-based decision engine to configure this online depending on the image, application, and constraint. And we are able with this configuration to navigate the different fidelity bandwidth trade-offs. In our experimental results, we show that our solution achieves and improves the state-of-the-art performance in terms of bandwidth savings and perceptual fidelity. And as future work, we plan to expand the comparison with other semantic communication benchmarks. We would like to improve the characterization of the decision engine. We will improve and explore other alternatives for the path selection procedures, and we will automate the ranking of semantic categories. I hope you enjoyed the presentation, and thank you very much for your attention.